Hi, so in this video and for the next couple of videos, we're gonna discuss some differentiation questions and at the same time we'll revise some of the concepts that some of you might have forgotten because it's been so long since we have done any differentiation questions, right? To start it off, this video we would just be doing the differentiation technique questions, no application involved, so just plain old differentiation. So let's just start off with the very first question here from JJC 2012, promo question 7. Given that x squared minus 6xy plus 2y squared minus 21 equals to 0, find dy dx in terms of x and y. So for this, you realize that on the left-hand side of this equation, everything is jumbled up. There's x and there's y involved. So clearly we have to use implicit differentiation here. So let's just go ahead and do that. So let's start off with writing the question, 6xy plus 2y squared minus 21 equals to 0. Now, differentiating implicitly, the first item would just be 2x. Differentiate this implicitly now with respect to x. Now you have to make use of product rule here. There is 6x and there is y. So you gotta use, we will hold 6x first and then we'll differentiate y. Differentiating y gives us dy dx. Plus, now do the other way around, we will hold y and differentiate 6x, which would give us 6y. And the next one, 2y squared is just 4y, dy dx, and minus 21 will just give us 0. And this side is still 0. Let's do some cleaning up. We will get 2x minus 6x dy dx, 6y plus 4y dy dx equals to 0. We will bring this and this over to the right hand side of this equation to give us 2x plus 6y equals to 6x dy dx minus 4y dy dx. Factorize out the dy dx. Whatever you have, we just put it underneath here, 6x minus 4y. We can simplify this further. This will be 1, 3, 3, and 2. That's it for the first question. 3 marks, very easy. So the next question is from CJC 2012. This question is almost exactly identical, nothing fancy, just find dy dx in terms of x and y. Once again, on the left hand side, you see a mixture of x and y. So clearly here, this is another case of implicit differentiation. So let's go. The first item here, e to the power of tangent inverse x. So whenever you differentiate e to the power of whatever, this would give you f prime x, and then you copy. So the item on top is fx. So we have to differentiate tangent inverse x and just put it in front, just like that. So the answer would just be e to the power tangent inverse x, and then we have to differentiate tangent inverse x. So how do we do that? All we need to do is visit our trusty MF26 here. So you see tangent inverse x, when you differentiate it, you get 1 over 1 plus x squared. So let me just put this aside. 1 over 1 plus x squared minus xy. Oh, sorry, we have to differentiate this, right? So once again, we will use product rule because there is x and there is y. So we will hold x, differentiate y, plus hold y, differentiate x, which is just 1. This is equals to 4. Okay? Once again, we just need to make this guy here the subject. And point to take note, notice e to the power of tangent inverse x minus xy is equals to 4. So if we were to start a mini side project here, right, e to the power of tangent inverse x is actually equals to 4 plus xy. Why we want to do that is because we want to make use of this and to replace this so it looks cleaner. So to go ahead, we'll write this 1 over 1 plus x squared, 4 plus xy. Oh, sorry, this is 0 because differentiating 4 gives you 0. My bad. This will be minus x dy dx minus y equals to 0. Bring this over. 4 plus xy over 1 plus x squared minus y equals to x dy dx. So dy dx would just be 4 plus xy over x, 1 plus x squared minus y over x. That's it. So we're done with the first part. Second part of the question is here. Let me just scroll down. Same kind of question, nothing very fancy. Given that y equals to 2x plus 1 to the power of x, for x greater than 0, find dy dx. Okay, so do take note. The function you see on the right-hand side is actually some interesting function. It's not a polynomial. It is also not an exponential, because for an exponential, the unknown is the power. And for polynomial, the base is the unknown. The base is the unknown. This is a combination of two. The base is an unknown, the power is also an unknown. So how do we do this? We have to actually rectify this by applying logarithms on both sides and forcing the power to come down. So let's just start off by writing it down. Y equals to 2x plus 1 to the power of x. Now we're going to apply logarithms on both sides. So we'll have ln y equals to x ln 2x plus 1. Now we will use implicit differentiation. Differentiating the left-hand side implicitly with respect to x would give us 1 over y dy dx equals to, so this side we have to use product rule once again because there's two items here. Hold x, differentiate this, we would get 1 over 2x plus 1 multiplied by differentiating 2x plus 1 gives us 2. By the way, ln of fx, just for revision's sake, differentiating this gives us 1 over fx multiplied by f prime x. So differentiating 2x plus 1 gives us 2. So we put a 2 in the numerator. Okay, so we held this, we differentiated this, now we do the other way around. We differentiate this, we hold this. We will get ln 2x plus 1. So once again, make dy dx the subject here. Dy dx would just be 2xy over 2x plus 1. I multiply both sides by y, by the way. And here I'll get y ln 2x plus 1. That's it. Okay, the next question, number 3. One more question before I move on to something more exciting. So number 3 is still a differentiation technique question. Nothing very fancy, just use the right technique, we will get the correct answer. So next one, differentiate the following with respect to x once again, and you simplify them. First one, it's differentiating ln of cosine x squared over 2x. I put the bracket here because this square is only applied to the x. It is not, there's a difference between this, which is cosine x whole thing square, and this cosine x square, which is actually cosine of x square. This is actually the second one, not this one. To do this, of course we can brute force it because we know that ln of fx is actually equals to f prime x over fx. But your fx here, it's pretty humongous. You can brute force it by writing, a fraction on a fraction, but that would be pretty troublesome later on. So the best way to do this would be to apply quotient rule of logarithms that you learn in Sec 3. This would give us d dx of ln cosine x squared, let me delete these, minus ln of 2x. And this would give us, let's differentiate the first one first. Ln of cosine x squared will give us 1 over cosine x squared multiplied by the differentiation of cosine x squared. So if you can't do this mentally, let's just start a mini side project. Let's differentiate cosine x squared, yeah? So to differentiate this would just be negative sine of the function, which is x squared, multiply by the differentiation of the content. This will give you 2x. So this is actually negative 2x sine x squared. All good? We're going to put this in. Negative 2x sine x squared. So we're done with this. Now differentiating this would just give us 1 over 2x. Differentiating 2x gives us 2. And of course, later we'll simplify this to 1 over x. So now, all we need to do is stack this on top. Sine x squared over cosine x squared minus 1 over x. Sine something over cosine something gives us tangent x squared minus 1 over x. And that's the answer for the first one. Oh, sorry, I left out the x here. Yeah, so that's actually an x. Part B, differentiating tangent inverse 2 plus x over 1 minus 2x. So let me just bring this down. So tangent inverse 2 plus x over 1 minus 2x. Point to take note, you can use the MF26 here. Let me just show it to you again. So MF26 says this. Differentiating tangent inverse x gives you 1 over 1 plus x squared. However, do take note that these MF26 formulas here are sort of a bait, okay? A lot of students think that, oh, let's say I have tangent inverse x. Differentiating this gives me 1 over 1 plus x squared, right? Oh, so if they give us an x squared here instead, for example, like so, tangent inverse x squared. Oh, all I need to do is replace this x by x squared. So they will get answers like this. 1 over 1 plus, x squared, square. 1 over 1 plus x to the power 4. This is incorrect because the formula they gave you in MF26 is actually the most simplified and the simplest case. You have to know the general case. The general case is actually this. So this is wrong. Let me just box it up. This is wrong. The correct version is this, dx of tangent inverse of fx. So this is whatever function they give you. This is equals to f prime x over 1 plus fx squared. You have to know this one. You can refer to the MF26 if they give you the basic one. Take note here, you look at this fx. The one they give you, the fx is just simply x. And what happens when you differentiate this fx? Differentiating x will just give you 1. See, that's why there's a 1 here. This is not the generalized formula. The generalized formula is actually this. If you have fx, the differentiation, you put it on top. So let's use this knowledge here to actually solve this question. So using this generalized formula, this question becomes rather simple. Now, I know you might be thinking, oh, what if I let this be y, right? Tangent inverse 2 plus x over 1 minus 2x. Then tangent y must be this. Then why don't we do it implicitly, right? It looks easier. However, it's actually not, because this will give you secant y dy dx, and this will be a nightmare to convert later, right? Because this y is actually this. So secant square y would be secant square of tangent inverse 2 plus x over 1 minus 2x. It's a horrible conversion to do later. We will not use this strategy here. Let's just brute force it, because sometimes the only way to do it would just be to brute force it. So let me just copy down the question here. Tangent inverse 2 plus x over 1 minus 2x. fx here is actually this fraction you see. So differentiating this would give us the differentiation of this. How do we differentiate a fraction? We will use quotient rule. 1 minus 2x squared, whole bottom, differentiate top, which will give us 1, minus, we will hold top, we differentiate bottom, it will give us negative 2. This will be the differentiation of fx, which is f prime x. And then at the bottom, all we need to do is 1 plus, whatever this is, squared. 2 plus x over 1 minus 2x squared. So here you start to see something in common, right? That 1 minus 2x whole thing squared. So what I'm going to do now is multiply the top by 1 minus 2x squared and the bottom by 1 minus 2x squared. This will give us, let's simplify the top first. This will give us 1 minus 2x plus 4 plus 2x over, because the denominator is gone, because this cancels off with this, right? This will cancel off with this, and the 1 will become 1 minus 2x whole thing squared. So at the numerator, you will get 1 minus 2x whole thing squared plus 2 plus x whole thing squared. Simplify this will give us 5, and at the bottom, to simplify this, I think we have to actually expand it. So let's just go ahead. 1 minus 4x plus 4x squared plus Oh, we have to extend our fraction line. Plus 4 plus 4x plus x squared. This will give us 5 over 1, 4. 5, 4x and 4x gone, plus 5x squared. Then this will give us, we factorize out the 5 from the denominator. I'll get this, right? Which would give us 1 over 1 plus x squared. Now, such a coincidence that differentiating tangent inverse of this actually gives us exactly the same item of differentiating tangent inverse x, which is 1 over 1 plus x squared. Final question of this video, slightly more interesting. We actually have to do some application here because they say proof by differentiation fx is strictly increasing. So what this means is for the graph to be strictly increasing, like this, or like this is fine, right? This is, however, it's not strictly increasing because it goes up and it comes down. So this is not strictly increasing. So what are they trying to say here when they say f is strictly increasing? What's so special about this kind of graph? Notice that the gradient is always positive. No matter how I draw the tangent line, the tangent is always positive. So in other words, this translates to dy dx is positive. So knowing this, of course, we will go ahead and start finding dy dx. So if fx is actually just x cubed ex squared plus x. Differentiating this would just be applying product rule here because there are two items. We will hold the first one, we differentiate this. Differentiating this just gives us 2x ex squared plus, do the opposite, we will hold e to the power of x squared, we differentiate x cubed, we get 3x squared e to the power of x squared plus 1. Let's clean this up. We actually get 2x to the power of 4 ex squared plus 3x squared ex squared plus 1. So if we were to factorize out x squared ex squared, it will leave us with 2x squared plus 3 and then plus 1. So they say proof by differentiation, this item here, dy dx, is always positive. So how do you show that this is always positive? Very easy, because this item here, always positive, right? Because x squared, square values are always positive. Second item, e to the power of x squared, any exponential function is always positive, right? So far, we have known that this is positive. Secondly, this is always positive. Third, look at this. 2x squared plus 3. This is definitely a positive number. Multiplied by 2 will always give you a positive number. Adding 3 to it will still give us a positive number. And finally, the cherry on top, the plus 1. This is also always positive. So no matter what x value it is, this entire thing here, it's always positive. Now, of course, you've got to write this in words lah. Since x squared, always positive, e to the power of x squared, it's always positive, 2x squared plus 3 is always positive. Therefore, f prime x is always positive, which means that f is strictly increasing. That's it for this video. Thank you.